We're going to discuss inner product spaces. Now, when I say the words inner product, you probably think of the scalar product in Rn. What we're going to do in this video is we're going to define an inner product more generally. And an example of an inner product will be the scalar product in Rn. So suppose you have a vector space V, and it's over the field of real numbers. An inner product is a mapping that takes a pair of vectors x and y and assigns to that pair a real number. And this mapping has to satisfy three conditions. The first condition is that when you take the inner product of a vector with itself, it has to be greater or equal to 0. And the only time that the inner product of a vector with itself is equal to 0 is if the vector x is equal to 0. The second property is that the inner product is symmetric. If you take the inner product of x with y, you're going to get the inner product of y with x. The last property is that if x, y, and z are vectors in your vector space, and alpha and beta are two scalars, then alpha times x plus beta times y, if you take that vector and take the inner product of that vector with z, you get the inner product of x with z times alpha plus the inner product of y with z times beta. So this inner product is linear. You can take this sum, which is a sum of vectors, it becomes a sum of real numbers, and this real number and this real number can come outside of your inner product. Now, because the inner product is symmetric, you could also put this alpha x plus by as the second part and put the z here. So you can write something like x alpha y plus beta times z. This also breaks up just like this one. So it's actually linear in both parts, the part before the comma and the part behind the comma. Let's look at some examples of inner product spaces. The first example is just the scalar product in Rn. So for x equal to x1, x2, all the way to xn, and y equal to y1 through yn, the scalar product is defined as x transpose times y. Now we can check all of these properties. The first property was that the inner product of a vector with itself is always greater than or equal to 0. Well, let's check. This is equal to x transpose times x, which is the dot product, or the scalar product, so it's x1 squared plus x2 squared, all the way to xn squared, which all of these numbers, so when you square them, they're going to be 0 or positive, and then you're going to add numbers that are 0 or positive, so it has to be greater than or equal to 0. And it also makes sense that the only way for this to actually equal 0 is if each one of these is equal to 0. Because if one of them's not equal to 0, then there's no way to subtract, like if this was a 1 here and 1 squared is 1, there's no way to get rid of that 1. So they all have to be equal to 0. The second property was that the inner product is symmetric. Now you can check that. You just need to check that x transpose y is equal to y transpose x. And that's obvious because x transpose y is x1, y1, all the way to xn, yn, and you can switch the order. So you can make this y1, x1 to yn, xn, but that is y transpose times x. The third property is that the inner product is linear, and we can check that as well. That actually shouldn't be hard to check. You just want to check that alpha x plus beta y with z is alpha x with z, beta, the inner product of y with z. Well, by definition, this is alpha x plus beta y transpose z, and now you just use properties, the property of transposes, which is it distributes over a sum. So this is alpha x transpose plus beta y transpose times z, which is alpha x transpose z plus beta y transpose z, which is alpha times the inner product of x with z plus beta times the inner product of y with z. So it passes all of the properties of an inner product, so this is an inner product. Now you might want to know what other types of inner products you can come up with for the vector space Rn. And this is actually interesting. They all take the same form. So to tell you what the form is, I have to first define to you what a positive definite matrix is. Now a matrix P, that is a square matrix in Rn times n, is positive definite if it satisfies this property, which is very similar to the first property of the inner products. It says that this matrix is positive definite if x transpose times p times x is greater than or equal to 0 for all x in Rn, and if x transpose p times x is actually equal to 0, implies that x is equal to 0.